In section 5.2, we will examine logarithmic functions. First, we have to talk about what a logarithm is. But in order to talk about logarithms, it's important for us to understand exponents and exponential equations. Let's start with a simple example that we can all easily relate to. If I were to write 3 squared equals 9, there are 3 parts to this equation. The number 3 is the base of the power. The number 2 is what we call the exponent. And 9 is the result. If we were to rearrange these 3 parts, we could write them as a logarithmic equation. Let's look at the meaning of the logarithm base a of x in the first box. For x greater than 0 and a positive constant other than 1, the logarithm base a of x is the exponent to which a must be raised in order to get x. In other words, logarithm base a of x is asking, what does a have to be raised to in order to get the result x? In other words, the answer is an exponent. So, a logarithm is an exponent. It's answering the question, what exponent must I place on a base of a in order to get the result x? Look at how the statement a to the mth power equals x compares to what we wrote above. In this case, the base a is 3, m, the exponent, is 2, and x, the result, is 9. We can rewrite these 3 parts as a logarithm as follows. We can say the logarithm base 3 of 9 is equal to 2. This is because we're simply rearranging those 3 parts. The base 3 is the subscript of the logarithm. 2, the exponent, is what the logarithm is equal to. And 9, the result, is what we call the argument. So again, a to the mth power equals x can also be written as logarithm base a of x is equal to m. It's simply taking those 3 parts and rearranging them in another order. In this example, we started with a base of 3 for the logarithm because this is a base that we could all easily relate to. Well, there are 2 other bases that are very common in mathematics. Because we use a decimal system, which is a base 10 system, it makes sense that we would talk about logarithms that have a base of 10. These are actually called common logarithms. So a common logarithm has a base of 10. In fact, if we were to write the logarithm of x with no explicit base, it is understood to be a base 10. Similarly to how we don't write multiplication by 1 explicitly, it's just implied, or we don't write exponents of 1, that's implied as well. When we don't write a base for our logarithm, it's understood to be base 10, and this is referred to as the common logarithm. Another very well-recognized base in mathematics is a base of e, where e is the Euler constant, which is an irrational number with an approximate value of 2.71. We saw this in our earlier section. When we have a logarithm base e, we write that as the natural logarithm, or ln for short. So a logarithm base e of x can be written as ln of x. Again, this means that the base of the logarithm is understood to be e. To To practice this concept, which may be new to many of you, we're going to practice rewriting some of the following exponential equations as logarithmic equations and vice versa. Converting between the two forms will help you practice how to rearrange the three parts. Let's look at example 1. Logarithm base square root of 5 of 625 equals 8. So the base here is the square root of 5. The exponent is 8. And the result is 625. You can use any scientific calculator to verify that when you take the square root of 5 and raise it to the 8th power, we get exactly 625. Next, we have logarithm base f of x minus 6 is equal to 7. The base is f, the exponent is 7, and the result is x minus 6. Next, let's practice going in the opposite direction. So we have some exponential equations that we're going to rewrite as logarithmic equations. We have 512 is equal to 8 to the 3rd power. Here the base is 8, so we'll say logarithm base 8. The result after applying the exponent is 512, so that will become the argument. And the exponent is what the logarithm is equal to. Here the exponent is 3. Next we have 1/2 to the v power is equal to 8. So we'll write this as logarithm base 1/2. And the argument, the result, is 8 equals the exponent, which in this case is v. Next, we have e to the t power is equal to 10. So the base is e, so we'll write logarithm base e. The result, the argument, is 10 equals the exponent, in this case t. As we said earlier, logarithm base e can also be written as the natural logarithm with no subscript, so we'll say natural logarithm of 10 is equal to t. Let's look at some properties of logarithms. For any logarithmic base a, the logarithm base a of 1 is equal to 0. And this is easily verified because a to the 0 power is equal to 1 for any non-zero base a. Another property is that the logarithm base a of a is equal to 1. Again, this is also easy to verify because rearranging the three parts would give us a to the 1st power is equal to a, which is a true statement. Let's apply some of these properties to the following examples. Logarithm base 4 of 4 is equal to 1. I'm going to say because, and I'm going to use this BC abbreviation for because 4 to the 1st power is equal to 4. Next, we have logarithm base 9 of 1. Well, this is going to equal 0 because 9 to the 0 power is 1. Next, we have logarithm base 3 of the 4th root of 3. Well, let's rewrite the 4th root of 3 as 3 to the 1/4 power. Well, logarithm base 3 of 3 to the 1/4 power will be 1/4 because 3 to the 1/4 power is equal to 3 to the 1/4 power. Again, notice what we're doing here. We're writing the base, exponent, result. Logarithm base 7 of 1 over 7 will be -1. This is true because 7 to the -1 power is equal to 1/7. Logarithm base 4 of 4 to the 7/2 power will be 7/2. I think you're getting the gist of it now, or hopefully you are. This is because 4 to the 7th half power is equal to 4 to the 7th half power. Again, we have base, exponent, result. Logarithm base 5 of -1. What power of 5 would give us -1? Well, this one does not exist. One of the requirements that we saw in our introduction of this section is that the argument introduces x above. The argument must be positive. So you cannot have a negative argument, a negative result. That means that this logarithm does not exist. Logarithm base square root of 7 of 49 will be equal to 4. And that is because the square root of 7, when raised to the 4th power, becomes 49. Next, we have logarithm base 2 of 8. Actually, this is number 7. I should have done this one before number 8, but that's okay. Logarithm base 2 of 8 will be 3. And this is because 2 to the 3rd power is equal to 8.